in the case of elliptic integrals, it's a polynomial of degree 3 or 4. It's too complicated in a sense. So first, consider the simplest case, square root of z. What is this? Well, of course, it's a number such that square is set. So if W is not 0, or that is not 0, then we have two roots. And the problem I said is, which should we take? Okay, one of the ways to avoid such ambiguity is to restricting argument. I mean, if we use the polar expression for the complex number z, square root is just like this. Is it okay? Well, everything changes. Oh, good. Not exactly, because argument is not a single valued function. If our argument of z is 5, then we can add or subtract 2 pi, 4 pi, and so on. So accordingly, square root becomes, well, this part is okay, of course. Or this is also square root, and actually this is just minus square root. So in other words, this problem of plus or minus is a reflection of the ambiguity of the argument. So usually when we compute, for example, complex integral in complex analysis, one solution of this ambiguity is restriction of the argument. For example, we often use such argument. And And well, in most cases of computation of complex integral, contour integrals, such method works well. But not always, because we have some gap here when we cross the negative part of the real axis. The argument jumps abruptly by 2 pi. So argument is not continuous function. Moreover, this choice is quite arbitrary. For example, this is another choice. Or, maybe we can use this and so on. This is quite inconvenient because later we will consider integral contour integral, and contours would move quite freely. So in such a case, fixing the range of argument is not very convenient. So instead, we use Riemann's idea. What is that? Well, if we consider square root on the domain, which does not include 0 and sufficiently small, we obtain 2 possible values. So let's split this domain into 2. Since we have 2 values, let's define each of them on a different domain. Correspondingly, name each point in this domain z plus, for example, here z minus. And assume that the argument here can be defined or chosen uniquely. Not defined, choose, and continuous. So we can reasonably choose argument z so that this part is a continuous function. Then let's define square root of, so to say, upper z by this. Since we are choosing one argument, this is well defined and continuous function. Correspondingly, the lower z has square root minus of this one. Okay, if D does not contain 0, then it's okay. And of course, this is always uniquely defined because such W, yes, is only one. Пожалуйста.
Вот что значит Z плюс и Z минус, я не очень понимаю.
Это, yeah, this is just a definition of certain set. D plus is just such a set with some sign, some additional data. For
Что за область?
Просто взяли область и каждую точку проиндексовали плюсом. И сделали еще такой проиндексовали минусом.
So we have to.
Просто мы взяли их, размножили на еще две части.
Значит, нам надо два одинаковые точки. И нужно разрешить. Поэтому сейчас добавляем плюсы и минусы здесь. So we need 2 points for this and this. So in order to distinguish them, we just added some additional data. So in a small region, it's okay. At 0, square root is always uniquely defined. And then what should we do with the whole complex plane? Well, So in this case, we cannot choose the argument continuously as we discussed, so let's cut it. For example, like this. Then and we need two such sheets. So let's call this one C plus, this C minus. And we want some good square root, especially continuous one. So as we saw, if we cross this negative part of the real axis, then it becomes discontinuous. That's not good. So we paste two sheets in this way. So let's consider zeta in this form. Then let's start from here. Here phi is equal to 0, and here up to correspondingly on this sheet we use this definition. So here. And at this point, square root becomes, since here is pi, we have square root of and if we come here, we have something like this. What is this? It's minus I, because the so that's why this becomes discontinuous function. Here, if since on this sheet we are using this definition, so correspondingly we have here we have minus of this, and here we have therefore if we cross this line and go not here but jump to this point, or contrary, if we come here, then if we go to this, sorry, if we come here, then we go to here. then it becomes, square root becomes continuous function of phi. From here, at this point we have this value, at this point we have this value. So we connect these 2 points. So the resulting field here is something like this. Here we have probably it's not very easy to understand, but this part is here, and it is connected to this side. This and so. So this is a good place where square root can be defined quite reasonably, continuously, and so on. Namely, let's call it. And zero is always exception because we have always just one square root of zero. So this is the replacement of the complex plane in order to define the square root. And on this part, as we saw, this and here. So this space R is called the Riemann surface. In this case, of square root z. Is it okay? So, let me repeat. There are two possible values of square root. So we need two sheets. And to get a continuous, in a sense, function on this set, we need to glue two sheets in this way. This is the Riemann surface. Actually, this is maybe too handmade, naive construction. Another more systematic, but maybe hard to say what is happening, is the following. So we used, as you asked, something like this, z plus and z minus. As I told you, we need this plus and minus to distinguish two possible values of square root. Then why not use square root itself? So, okay, it's a bit tautological definition, but reasonable. And actually this is better maybe let's define R as a set of pairs of complex numbers which satisfy this equation. Probably, at this moment maybe it's a bit crazy, but well, this might seem more mathematical. This is better description, for example, in this sense. Well, we have to subtract 0 as an exception and added 0 later. But in this case, in this description, 0 is all naturally included, just as 1 point. And you can introduce topology, for example, on this set by gluing topologies on this space and on this space and suitably defining a neighborhood of 0. But in this case, it's a subset of C2, so we have a natural topology as a subset of C2 or R4 if you like. And the punchline is that this R is a complex manifold. So probably all you from HSC know what is a complex manifold, but maybe for those who are coming from other countries need some explanation of this, so let me recall you what is a manifold. So real manifold is often abbreviated in this way, is, well, I do not use this condition, but it's a Hausdorff space. There is a local coordinate system, well, atlas. namely X is covered by open sets, and each open set has a homeomorphism to some open subset of Rn. And we need some condition for intersection. So phi mu is a homomorphism between U and V here. Phi lambda is a homomorphism between them. So we have two images of intersection. And so we have homomorphism between these intersection and these images of intersection. And condition for this homomorphism defines the property, the class of this manifold. So if this map is C out cross, then X is called CR manifold. If this is analytic function, then it is analytic manifold, and so on. This is a usual definition of the manifold over R, and if we replace Rn here to Cn and requiring this homomorphism to be holomorphic, then it is a complex manifold. So what we have defined was this set in C2. Actually, this becomes a complex manifold. And let me state one general theorem. Let f be a polynomial in two variables. Well, actually, f can be a holomorphic function, but well, what we use is just polynomial. And let's assume that f and its derivatives do not vanish simultaneously. Yes.
Вы сказали, что R это одномерное многообразие. Почему оно одномерное?
This one. Это
R.
R.
Да, почему оно одномерное?
Одномерное. Это n-мерное.
Нет,
Вот это, да, одномерное.
почему?
Потому что у нас есть два координат и есть одно условие. 2 минус 1 это 1. Yes, сейчас объясню. This theorem will answer you probably. Let's assume that these conditions. Okay, yeah. Then the set of solutions of this equation becomes on U, I mean. Becomes a one-dimensional complex manifold. Maybe, in this case, maybe it's not connected, but it's not important here. This is a consequence of the implicit function theorem. In this case, well, let's assume those conditions. And let's take one point where f vanishes and partial derivative does not vanish. Then if we take sufficiently small regions around this point and around Z, like this. This is a subset of this set. Then projection from here to here. Anyway, just take the first coordinate. This is bijective. So, well, if we take Z here, then we can find W here. And so let's call the inverse mapping like this. So, well, the first component does not change. So from here we have something like this. Then the second component, phi, is a homomorphic function. This is the implicit function theorem in this case, in the complex region. And well, yeah, I hope you know the implicit function theorem over R very well. Is it obvious? Is this theorem obvious from that real implicit function theorem? Not quite, because, yeah, for example, we need to show homomorphicity of this part. Or actually, since F is a complex number, this, Z and W are complex numbers. In the real world, it's a F is a mapping from R4 to R2. Why R2? This is the value of F is a complex number, so it's two-dimensional. So in this case, the implicit function theorem needs some condition of non-vanishing of Jacobians and so on. So, well, of course, we can use real implicit function theorem to prove this theorem, but with the help of those Cauchy-Riemann equations. For example, to show homomorphicity or to show the non-vanishing of the Jacobian. But, well, yeah, since we know, at least I hope you know complex analysis well, we can show this theorem, this implicit function theorem, just using argument principle. How to do that? Well, first let's fix the first component of Z. And assume f as a polynomial in W. Then by this assumption, this is 0, and f prime is not 0. This means that f has a Taylor expansion like this. Actually, it's a polynomial, so it ends truncates at finite term. But anyway, if we restrict W in the neighborhood of W0, f vanishes only here. And therefore, by the argument principle, such an integral is equal to 1. So for example, if f has double 0 at W0. So WC minus W0. Or exactly speaking, doesn't. Let's integrate this function on a small circle around W. Then it is 1. And so on this circle, we can assume that f does not vanish. Since in the neighborhood of this point, there is only 1 0 here, so we can take such a rule that on this circle and on this disk, the only 0 of f is W0. So And since f is a continuous function, this condition, namely this condition holds even when z is not z0, if z is sufficiently close to z0. So we do not perturb f much. And if we define a function n as a number of zeros of this equation, in this region. For example, z0 is by this consideration 1. And in general, by the argument principle, it is all expressed in this form by integral. And this is a continuous function. Well, yeah, exactly speaking, this is a continuous function of z and w, and we are integrating this on a compact set, and so this becomes a continuous function of this argument, this parameter. And of course, this is a number of zeros. It is just an integer or natural number, actually. N takes values in z, in n, if you like, and it is a continuous function. Then what a function is it? Constant. Exactly. And since at z0 it's 1. It is always 1 if z satisfies this condition. So what does this mean? This means that there is only one zero of this polynomial in W. Z in this region. There's just one W. So we have a bijection between them. And actually we can express this W as an integral of this type. So we want the expression for this phi, and actually it is expressed in this way. So if there is no W here, it is an argument principle. This is 1. So this is an application of the generalized argument principle. Do you know this? Yeah, also. Such an integral expresses the sum of this function at zeros of this function in this disk. This is the generalized argument principle. And here we have just one, as we have already shown, there is just only one zero here. So we do not have to take sum. And here we have W, which means that we get Wi itself, namely the position of the zero is obtained by this integral. And again, we have an integral expression of this function, which is whose integrand is holomorphic. Integral of a holomorphic function over some compact set is a holomorphic function with respect to this parameter. That's the proof of the complex holomorphic implicit functions. So locally we have a holomorphic correspondence of this type. So if we take a neighborhood of each point, then the projection from here to here is bihomomorphic, which means that it is of course homomorphic, and this map is homomorphic. So we can use such atlas, and from here it follows that R is a complex manifold.
Excuse me, but the correspondence is holomorphic only at the points where gap over GW isn't zero.
Yeah. So. And it's you will. Thank you. If it is not zero, then we have this local coordinate. Good point. Yes. So I'll say that. If this is not zero, then let's take some neighborhood of U1 where this condition was. And in this case, let's exchange the rows of Z and W. Then we can use the projection to the second component as a local coordinate. In this case, the first component can be recovered holomorphically. So, if this is not zero, then we use this. If this is not zero, then we use this. And if both of them are zero, then it is not zero, so it is excluded already. So therefore, we can use, or there is a one-dimensional, which means that we have just one C here, one-dimensional complex field here. So we have one coordinate, here Z, here W. Therefore, it is one-dimensional complex manifold. So, well, in algebraic geometry, which I don't know quite well, I do not know well, such R is called non-singular algebraic curve. Non-singular because there is no singular point. Algebraic because F is polynomial. Exactly speaking, we have to add affine or something like that, but probably you know better. And curve because it is one-dimensional. Oh, sorry. Let's do it. So, yeah, let's apply this theorem to this polynomial and study in the structure of the Riemann surface of square Z next time. Today we do not have homework problems.